Alrighty, geometry folks, today we're going to be talking about Pythagorean theorem. If you were in class, you should have already went through this. You could use this as a reference. Excuse me, after we finish this sheet, we are going to work on some examples so you can stick around for us. And we're also going to talk about the converse of the Pythagorean theorem a little bit at the end of this video as well. So, for starters, the Pythagorean theorem allows us to find the third side of a right triangle. Keywords being right triangle here. It has to be a right triangle. If we know two of the triangle's side lengths, then we can find that third side. Did you know that the sides of a right triangle have special names? Two sides that form the right angle. So if we have a right angle here at A and B, these two sides would be the legs. And the side across from the right angle is always the longest side. We call that the hypotenuse. Most of the time, we're going to call it C. So, for example, if we have a right triangle like such, we would have a leg here, a leg here. These two legs make up that right angle, and across from that right angle, we would have the hypotenuse. Most of the time, we'll call this A, B, and which we can interchange, and this is almost always going to be C. So part one, identify the leg and the hypotenuse of the right triangle below and label its side lengths of the legs of the triangle. So here we would have A and B would be our legs. So leg A is 1, 2, 3, 4 units in length. Part B, 1, 2, 3, leg B is 3 units in length. Next it says, on the grid below, create a square from each of the legs so that each square shares a side length with the leg of the right triangle. So we're going to create a square based off this leg. And we learned last unit that squares have all sides, all four sides are congruent. So if this side is 4, then we need to have each other side be 4. 1, 2, 3, 4. Another square coming off of there. 1, 2, 3, 4. 1, 2, 3, 4. And we've got a nice, you can shade it in here, square coming off of A. And we're going to do the same exact thing here with B. So on B, we got 1, 2, 3. So each side length is going to be 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. And there is our square coming off of B, just like we have the square coming off of C. Next, it says find the area of each of your new squares, then find the sum of these squares' area. So the square of side A is, well, it's a 4 by 4 square. So 4 times 4, we get 16 square units. And the square of side B is 3 by 3. And we can even count 1, 2, 3, 4, 5, 6, 7, 8, 9. But we know 3 times 3 is 9. And the sum of these, 16 plus 9, that gives us 25. Okay. So now we're going to compare the combined area of these two squares to the side C square. Side C square has been copied down and rotated and lined up for our grids. So let's take a look at side C. Well, side C is square is 1, 2, 3, 4, 5 by 1, 2, 3, 4, 5. And again, we can even just count our square units inside here. 1, 2, 3, 4, 5, 7, 8, 9, 10. We would get 5 times 5. This is 25 square units. Okay, well, let's take a look here. What do we notice about 16 plus 9 and the square units of C here? Well, 16 plus 9 is 25. So our area of A, or our square for A, plus the square of B is equal to the square of C. Okay, so let's keep going here. Scroll down a little bit. Okay, so the square to the left is the identical side square as the square of the hypotenuse. How do the areas of side square A, and I'm going to draw those again. Here's our A. Here's our B. We said this is 16, and this is 9. This is 25. How do the areas of the sides A's and B's square compare to the area of side C square? Well, square A plus square B is equal to the area of square C. Really, we say, okay, well, that's 16 plus 9, we know, is 25. How did we get that? Well, we know that side A is 4, so if we create a square there, it's going to be 4 times 4. Well, how else can we write 4 times 4? Well, it's going to be 4 squared plus 3 squared equals, wouldn't you know it, equals 5 squared. And this is going to be our Pythagorean theorem. And we can just plug in our generic values of A, B, and C, as we're going to see here fairly quickly. So if we repeated this process here and figured out our areas, we would find, okay, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Go 2, 3, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. By 1, 2, 3, 4, 5. So this would be a 12 by 12, which is 144, and a 5 by 5, which we just found out to be 25. This looks to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. By 13. What is the relationship between the legs of the hypotenuse and the legs of the right triangle? Well, we know 13 times 13 is 169, so we would see again that 144 plus 25 equals again 169. So part 3 says the Pythagorean theorem can be used to find the length of one side of a right triangle if we know the other two sides of the triangle. Pythagorean theorem is stated as a squared plus b squared equals c squared. Explain how the diagrams from part 1 and part 2 demonstrate the Pythagorean theorem. Well, if we square, we could just say that the square of a plus the square of b is equal to square of c. Because really, if we want to find the area of a square, we're squaring that length, whatever that length is. We said in here it was 12 and b was 5, and c would be, not plus, be 13, or c squared. And there's our Pythagorean theorem. We can, if we know it's a right triangle, we know this a side squared plus the b side squared is equal to, c side squared. Let me continue on here. It says, in parts 1 and 2, you were given leg lengths of a triangle and asked to find the length of the hypotenuse. How could you use the Pythagorean theorem to find the length when given the length of the hypotenuse in one leg? Basically, how could we use this to find a leg length if we know the hypotenuse length? Well, we've said earlier that square of A plus the square of B is equal to square C. Well, if we know square B and square C but don't know square A, we can just solve this equation, literally solve it for square A and subtract square B from both sides, which will give us square A is equal to square C minus square B. Well, how does that look for our actual Pythagorean theorem equation? Well, we said that the Pythagorean theorem is a squared plus b squared equals c squared. So if we know b and c, we can subtract that b squared from both sides and solve this. And we would know that that side length a squared is equal to c squared minus b squared. So if we know the two lengths, we can square them and add them together and get our c side squared. Or if we need a length of the leg, we can subtract. So let's look at a couple examples here. Okay, so A says, find the missing side lengths for each triangle round to the nearest tenth if necessary. So in this first one, we are actually given, let's start with example 3. So we know, let's start with 2. So here we want to find the hypotenuse, right? We know that this is the hypotenuse. And we have a leg here and a leg here. We know that a squared plus b squared equals c squared. So we can just plug in. Here's a leg. We can call this one A and call this one B. It does not really matter. So we could say a squared plus b squared. Well, we know b is 15 equals c squared. So now we're just solving. 8 squared is 64 plus 15 squared is 225. We know that that has to equal c squared. So now we add them together. 225 plus 64 gives us 289. C squared. Now to solve for c, we're going to need to take the square root. So if we take the square root of 289, we will get 17, and we would find that c is equal to 17. Or for us, it would be x is equal to 17. So that would be if we know two lengths of the legs, and we want to find the hypotenuse. In example 3, we're given the hypotenuse and a leg, and we want to find another leg. So really, if we set this up, a squared plus b squared equals c squared, we don't know this a squared. We can go a, b, c, but we do know b to be 8 squared is equal to 10 squared. So we would say, okay, now if we want to solve this for a squared, it's going to be 10 squared minus 8 squared, which we know is 100 minus 64. So a squared is equal to 36. Take that square root. We know that the square root of 36 is 6. So here we have an example of if we want the hypotenuse, a squared plus b squared equals c squared. If we want another side, we can subtract that length squared from the hypotenuse squared. Okay, so let's take this another step further here. Let's say, okay, let's use this Pythagorean theorem to state if it is a right triangle. Well, okay, let's do a little thinking here. If it is a right triangle, we know a squared plus b squared equals c squared. So we know that that has to be true if it's a right angle. Okay, so we know that our longest length has to be c, because the hypotenuse is always going to be the longest length. So if we say, okay, let's make this a and this b, then we can just plug in. Let's make sure 12 squared plus 9 squared has to equal 15 squared. And we know 12 squared is 144. We know 9 squared is 81. And we know 15 squared, we just found that out to be 225. Well, let's make sure 144 plus 81 is 225. So 144 plus 81 is indeed 225. 225 does equal 225. That is true. Since it is true, state if each right triangle is a right triangle. Yes, it is a right triangle. Why is it a right triangle? Because a squared plus b squared equals c squared. Okay, well, let's check this one. We know a squared plus b squared equals c squared. We know that c has to be our longest length, so c has to be 10, and then we can make either of these a and b. So we would say that we need to check that 8 squared plus 7 squared does equal 10 squared. Well, 8 squared is 64 plus 49 equals 10 squared is 100. We know 64 plus 49 4 plus 49 is 113 equals 100. No, it does not. That is false. So is this a right triangle? No, it is not a right triangle. So if it is not a right triangle, then it's got to be either acute or obtuse. So we can use what's called, and on the back side of this sheet is the converse of the Pythagorean theorem. And that states, okay, we can use the Pythagorean theorem, the regular Pythagorean theorem, to find these side lengths. We can also check if it's a right triangle using the Pythagorean theorem. As we did in A, we said a squared plus b squared does indeed equal c squared. But if it does not, we can classify it. So if c squared is greater than a squared plus b squared, then it's got to be obtuse. And if it's less, it has to be acute. Okay. And some things to kind of keep in mind here, we have some common Pythagorean triples. A Pythagorean triple is numbers a, b, and c who work for a squared plus b squared equals c squared. So there you have it, folks, a quick rundown of the Pythagorean theorem. If you need some extra help, please be sure to email your teacher and set up a time to work on this. There is a homework on Canvas, so go ahead and finish that up. Hope you have a great day. Bye.